We are learning some chemistry. It's time to learn more, you see. It's time for your warm-up. That was a parody of a song from the Muppet movie, which probably none of you have ever seen because you're all very young. That's fine. Let's do our quiz 1 warm-up together. I meant to underline that instead of crossing it out, but you know, whatever. I can erase. Okay. So hopefully you attempted this by yourself before watching this video. And if you did not attempt this by yourself before watching this video, then you need to pause this video and try it by yourself before you watch this video. Because if you're doing this quiz 1 warm-up, that means you have a quiz. And if you have a quiz, you need to be able to do it by yourself, or like you're gonna fail the quiz, because that's how quizzes work. So try it by yourself first. Pause the video, try it by yourself. Did you pause? Why have you not paused yet? You think I'm just gonna sit here and give you all the answers and then you're gonna pass the quiz magically without trying it by yourself first? Pause the video. Thank you. I am so proud of you for trying it by yourself. And for those of you who are lying to me and pretending you tried it by yourselves, enjoy failing your quiz. Okay. Let's talk about the heating curve first, which is this thing, right? This whole graph is the heating curve. It helps if you know where the solid, liquid, and gas sections are. Honestly, you don't have to have the whole dang thing memorized. But if you know where those 3 places are, solid, liquid, gas, you should be able to figure out the rest for yourself. So solids down here at the bottom, liquids in the middle, the gas is on top. It's those diagonals specifically that are solid, liquid, and gas. It's the diagonals, okay? Between a solid and a liquid would be how it changes to solid, or how it, from solid to liquid, or how it changes from liquid to solid. That's what goes in that section. Again, and between liquid and gas, how a liquid changes to a gas or how a gas changes to a liquid, that's what goes in that section. So that is just vocabulary words that, again, you hopefully already know from middle school. But really, if you know where solid, liquid, and gas are, then the rest of it would be something you should be able to think your way through with that wonderful brain of yours. For instance, solid and liquid together. Well, if 1 is just solid and 3 is just liquid, gee, where do you think both of them are going to be? How about in between? And that should make sense, because if you know that, like, when ice is melting, there's usually both ice and water in the cup. Oh, that's a solid and a liquid together. Ta-da! Liquid and gas together, both of them together. Again, if 3 is just liquid and 5 is just gas, where are we going to see both of them? We're going to see that in the middle, right between. Sorry, I keep redrawing my lines. Condensation, you have to know what that is. Condensation is a vocabulary word. That is when a liquid, oh, nope. That is when a gas changes to a liquid. I draw my L's as cursive lowercase, by the way. So that's an L. And this over here, that's an L. I'm sorry, that's just my handwriting that you're just gonna have to get used to. Anyway, when a gas changes to a liquid, oh, well, here's where a gas is, here's where a liquid is. The change would be happening right here in this section, which would be section number 4. Vaporization, also a vocabulary word you need to know. That is when a liquid changes to a gas. There's my lowercase l again. And again, if you know here's where your liquid is and there's where your gas is, then moving from a liquid to a gas is going to happen in between at number 4 again. Melting and freezing, again, these are vocabulary terms that you need to know. Melting is when a solid changes to a liquid, and freezing is when a liquid changes to a solid, more of my lowercase cursive L's. And if you know where your solid and your liquid are on the chart, then you know that probably the place where changes between those happen is going to be right in the middle at number 2. And finally, for compressible, most and least compressible, then that's going to be, do you know what that vocabulary word is? We talked about it. That word basically just means squishy. How squishy is it? The most compressible would be the most squishy. So if you're thinking like examples of a gas, think about the air inside a balloon. Okay. Example of a liquid, think of just like a lake. And then any solid, I would just go with an ice cube. Which one of those is the most squishy? It's going to be the balloon, which would be the gas, most compressible or most squishy. Whoops, and we want to write a number there. The number there is 5. Least squishy, which one of those is the least squishy? Is it going to be the balloon? No, because we just said that was the most squishy. It's going to be the lake. It's going to be that ice cube. So that's our solid, which is in section number 1. Okay, let's do some multiple choice. Which of the following states of matter have a definite shape, meaning the shape does not change when it's placed in a new container? So if I move a solid from one container to another, or a liquid from one container to another, or gas from one container to another, which one of those the shape will not change? I'm going to give you a hint that it's not going to be all 3 of them, because some of them are definite and some of them are indefinite. All 3 of them are not the same, definite or indefinite at any point. It's not going to be all 3. I'll even tell you that for number 3 right now too. It's not going to be all 3. So now we just have to think about shape. So again, I would just think of some examples of a solid, a liquid, and a gas. So going back to an ice cube for a solid, a balloon for a gas. Whoops, I'm writing in the wrong spot. Let's go smaller than a lake this time, maybe just like water in a cup for a liquid. And thinking about the shape. So a definite shape means the shape does not change. So if I think about the water in a cup, right now the water in my cup is shaped like a cylinder because my cup is a cylinder. And if I pour the water out of my cup, is it going to stay shaped like a cylinder? Am I going to get a cylinder of water in like the sink or wherever I pour this? No, it's going to take the shape of the sink and then like the drain and the pipes and so on. So the shape of the water changes, and that is the opposite of what this question is asking about. Though this question wants ones that don't change, so it's not going to be liquid. Okay, balloon. The gas inside a balloon. Can the shape of a balloon change? Yeah, that's like a party trick for like children's parties, right? Like, or like sometimes you go to Kirby Lane on a Sunday morning and there's like a person doing balloon animals, right? You can change the shape of a balloon. It's so easy. I mean, I can't do it, but people can do it. A person can change the shape of a balloon. Even like, I mean, I guess if I had like a balloon, I could just like squish it, right? And then the shape of the balloon would change. That means if it does change, that is indefinite. And again, this question was asking for something that doesn't change. So it's not going to be the gas. Solid, like an ice cube. If I had an ice cube in this hand and I moved it to my other hand, is the shape of the ice cube going to change? I mean, eventually it's going to start melting, but before it starts melting, is the shape of the ice cube going to change just because I moved it? No. So that means it doesn't change. That's a definite shape right there. A is your answer, buddy. Let's talk about number 3. Which of the following states of matter has an indefinite volume? Again, we can think of those same 3 examples, solid, liquid, and gas. So like going back to the liquid, to the water in my cup, this is a 1 quart cup. 1 quart. If I pour my 1 quart of water out of this cup and into a big old mixing bowl, is it still going to be a quart of water, or is it going to change how much space the water takes up? It's still going to be a quart of water. Water has a definite volume, which is not what this question is asking. So we're going to cross that out. Then we're down between a solid and a gas. If I think about an ice cube, and I move an ice cube from my ice cube tray in my freezer, move that into cup. Before the ice starts melting, does the amount of space the ice take up, does that change? No, this ice cube stays the same size until it starts melting. The act of moving it from one container to another does not change how much space the ice cube takes up. So that has a definite volume, which means solid's not our answer here. But a gas, like in a balloon, that volume can change. If you think about breathing, okay, I breathe in and my air is in my lungs taking up the amount of space that my lungs take up. But when I exhale that, I can get a balloon like pretty big off of one exhale, even though my lungs are not nearly as big as I can get that balloon to be. And that's because gases change their size to fit whatever container they're in. So the gas compresses to fit inside my lungs, it expands to fill the balloon. That's an indefinite volume, it changes. So gases have an indefinite volume. Let's do these two bottom questions. You combine potassium chloride and oxygen gas to form potassium chlorate. So here's your potassium chloride and your oxygen gas. Here's potassium chlorate being formed. That word form is kind of telling you that it's a product, which means it's on the right side of the equation. And then it asks, is this a physical or chemical change? Well, to answer that question, you have to think about the identity. Does the identity change? So if I look, I start with a compound, KCl. That's a compound. I also start with an element, oxygen. And at the end, I have one compound that is KClO3. So is this compound different from the stuff on the other side? And I would say yes. First of all, you can tell because they have different names. This says potassium chloride and oxygen, and this says potassium chlorate. That's a different word because that's a different thing. Plus, I mean, you can just look at it, KCl and separately the element O2. That's not the same thing as this compound KClO3. So the identity does change, which makes this a chemical change. You can abbreviate, that's fine. And then how do you know? Well, you could just tell me the identity changes. I don't need complete sentences here. You could also tell me that the products do not equal the reactants. You could tell me that. Those are the two probably most obvious ones from these this amount of information that we've been given in this problem. Okay, and number 5, you cool iodine gas creating solid iodine. Is this a physical or is it a chemical change? Well, we look and we see that our reactant is I2G, that G means gas, and our product is I2S, that S means solid. So we have iodine as a gas changing to iodine as a solid. And you have to, again, ask yourself, does the identity change? Well, if I have the element iodine at the beginning and I have the element iodine at the end, is that the same stuff at the beginning as at the end? And yeah, that's the same stuff. The identity does not change. If the identity does not change, that's a physical change. And why? How do you know? The most obvious would be that a reactant, here the reactants equal the products. Another way that you know that this is a physical change is because you have a phase change. A gas is changing to a solid. We even have a word for that. That's called deposition, my friends. There you go. Good luck on your quiz.